One thing that's of great interest is actually electromagnetic waves. What happens if you have an electric field? We set up an electric field before, we're talking about electric fields. And what happens if you change that electric field? If you have a change in your electric field, you end up with a wave. So basically, electromagnetic waves are a way of transmitting data or energy. So EM waves is general rule about EM waves is they basically travel at the speed of light, because after all, light itself is an EM wave. So they travel at the speed of light, which is approximately 3 times 10 to the 8 meters per second in vacuum. Remember, if it goes into different media like water or glass or diamond, then it'll travel at different speeds, and the ratio of the speed it's going to the speed in vacuum is the refractive index, basically. So what else can we say about EM waves? Unlike sound waves, do not need a medium. So what this means is EM waves will travel through space, which is really cool. Now, what type of EM waves can we have? Well, basically we visualize as an EM wave like this, traveling through. Usually it's going to be a sine wave. It's a crappy sine wave, I know, and this is going to be the amplitude of the power, but you'll notice that the power is changing. But that's because there's 2 components in there, and one of them is basically this is the electric field, but there's a magnetic field as well. And a magnetic field is going to be at right angles. We always consider it right angles. So if the EM wave is going this way, the magnetic wave is going that way. And both components will have energy. And if you add up the energy in the electric wave and the magnetic wave, it's going to remain constant, because as the energy drops off in the electric field, it turns into magnetic field. When it drops off in the magnetic field, it turns back into electric field. Isn't that cool? So these waves, well, we use these a lot. So what type of waves, EM waves, are there? Well, there's radio waves. And radio waves, these can be quite a large frequency, but if you listen to your AM radio, you might be listening to 1,000 kilohertz. Or, what was it? Kiwi FM used to be on 1,013 kilohertz. Which means that the wavelengths on that, how long's the wavelength on that going to be? It's going to be about 300 meters long. Which, yeah, you think about it. If you're building a radio tower, you need to build a radio tower at least at least as quarter of a tall as your radio wave's going to be. So that means your radio tower, if you're going to make a radio transmitter tower, has to be 75 meters tall. And you can see a couple of radio towers scattered out around Hamilton. If you go out towards Morrinsville on the back roads, you can see one out there. If you go out around the back of the Varsity, you can see the Radio Rema mast. So the wavelength is going to be 300 meters. If you've got an FM radio, you might be listening to 100 megahertz. And the wavelength of that's going to be about 3 meters. This is part of the reason why they like FM radios, because FM radio only needs a transmitter mast less than a meter tall. Other type of thing, microwaves that you cook with. I mean, microwaves are, well, you're going to be sub-millimeter, which is why micro. And then we get into light. Light is classic. And the wavelength of light is going to be anywhere from about 400 to 800 nanometers. And the frequency is going to be what, about, it's been a while since I've done light, about 4 to 8, 8 to 4 times 10 to the 14 hertz. And the thing is, the shorter the wavelength, the higher the frequency, the more energetic the light tends to be. So you get UV light in the many bands, and that's going to be what, 200 to 400 or 300 to 400 nanometers to -9 meters. Because this is shorter light, this has more energy, and that's why you get sunburnt. Then you get things like X-rays. X-rays have got really short frequencies, and so their frequency is like approximately 10 to the 20 hertz. So their frequency is a million times light, and we'll go through stuff like this. And then you get the big guys, the gamma rays, now, and cosmic rays, and these tend to have insane frequencies, hertz up. And so of these we actually use a lot. We use radio waves, we use microwaves, and sometimes we use microwave for transmission of power. In a microwave oven, we stick it in, go push 5 minutes, bing, it's boiling hot. Sometimes we use it for transmission of information, like microwave transmitters. So the thing about waves is, because these are so important, a guy called Maxwell, one of the great physicists of all time, came up with Maxwell's equations. And there's 4 equations, and these were invented in the 19th century, so this is before quantum and relativity. And these 4 equations we still use as the fundamentals of working out radio waves and light waves and such like that. So yeah, Maxwell's equations are the fundamental. We have tweaked them a little bit now that we know about relativity and quantum and such like, but Maxwell's equations are way beyond the level of this course. Maxwell's equations are usually done as a second year paper. So unless you're going to do second year, I think we'll call it a day on the waves, EM waves. The thing you have to remember about EM waves do act like ordinary waves. They exhibit the same behaviour. EM waves can diffract, they can refract, they can do, you can get interference, constructive, destructive interference, because they act like waves. But unlike sound waves, longitudinal waves don't need a medium. They can go through space. They can also go through glass and through air and things, but they don't actually need to travel through something. And it's true, in space nobody can hear you scream unless you got your radio on. So